Again, hello everyone, my name is Nicolo Brandizzi, and today I'm here to present the Emergent ImageNation project, which combines the emergent communication field with images. But first, a little bit about me. So I got my bachelor in automated engineering at Sapienza in 2017, and then I went for master in artificial intelligence and robotics in 2020. And now I'm doing my second year PhD in multi-agent reinforcement learning. All while I'm also the student representative of my faculty, and I'm doing, as Miguel said, a research visit in UVA in Amsterdam. So on the social activity, I'm a Rotary member since 2017, where we have many projects going on. Check out our website, it's really nice. And also a ESN volunteer since I was in Erasmus in Groningen, and a AD member since 2021. And hobbies, yeah, like the best thing is just my cat, which I find really cute, and I also have a picture over there. So let's start on my view of human communication. And we'll start with saying something really trivial, which is human communication is mostly grounded on vision. So as you can see here, there are plenty of pictures of kids pointing at objects, and usually with either a caretaker or other fellow kids, they refer to the object in the world by pointing at them. So it is obvious that in order to dialogue, to discuss new ideas, and also just to comment, we have to focus the interlocutor attention on a specific area of the real world environment, which is in this case done by pointing. But what happens when there is no actual common visual ground between two humans? So in this example, we have a girl saying my cat is a Bengal. And what happens is that the guy's mind just has this kind of imagination part, which is still a visual context, but it's referring is in a more abstract way. And so we can see that as humans, we do not have the ability to share these kind of internal vision representations, but we do find them really indispensable, necessary for communication, either when they're grounded in something which is in the real world, or they're internal and kind of in our mind. So I really want to show you a nice cut from a movie, Spirited Away. So in here, Haiku is actually telling Chihiro where to go. And as you can see, he's projecting to her mind the navigation path towards the boiler room, together with some textual information where he explains what to do. And I find this to be the optimal navigation task, shared navigation task, because you can use both images, which are like this, the images projecting to her mind, but also textual information, which is always necessary in order to explain better. So, but yes, this is mostly a magic-based communication approach, and we do not have magic for now, but we do have artificial intelligence, which comes close sometimes to what we can think of as magic. And so let's have a little background on the field of emergent communication. But let's start first with reinforcement learning. So for the one of you which are not familiar, reinforcement learning comes from psychology, and it's actually a learning paradigm. It usually involves an environment which states, so the environment state, how it behaves, how it currently is, it's expressed through observations. And this state can actually be changed through actions. And what does this environment experiment on itself? It does experiment the learning policy by an agent over here. The agent interacts with the environment, trying to maximizing the rewards by choosing the correct actions. So this is the whole field of reinforcement learning, really briefly, and just in like say a quick overview. And so let's say what the emergent communication field has to say about it. So as you can see, the image from reinforcement learning is the same. And with the emergent communication, you just split the agent in two parts. You have a sender, which has access to the observations over there, and a receiver, which can act. And so as you can see now, it becomes a task with two agents with a really important need to communicate between them, as one can just sense and the other one can act. And so you let them, as before, you let them cooperate and communicate through a message. In this case, the message can just be a vector of vocabulary V and length N. And you let them communicate in order to achieve the maximal reward as it was before. And usually you have that in these cases, the environment is grounded on a visual dimension in order to constrain both the sender and the receiver to a common ground. And this is really similar to what we experience as human beings. And indeed, some of the peculiarities of our language can also be seen in the emergence of machine language. So, but why? We as human, we do not learn languages by reading Wikipedia, obviously. And I advocate, but also the whole field advocate that learning a language involves interaction with other humans or other beings in a shared environment. And this interaction must be cooperative, usually are cooperative, they require some explainable decision making. And obviously, and this can be done, can be seen under two lights, the cooperation part, which I just talked about, but also on the language part, where we can actually study language emergence under a more similar setup than the one we use for now for standard language models, where they just read Wikipedia. So a referential game, yes, the most iconic game environment you can see in the emergent communication field is the referential game. So over here, you have an image, a target over on the left, which is a pencil, which is shown to the sender. The sender then has to come up with a message that refers to some properties of this pencil and pass the message to the receiver. Then the receiver is shown a pool of images, one of which is the original target and other are just distractors, and is tasked to choose the target image, which was shown to the sender. And this is the most iconic game environment you can find in emergent communication. It's studied and used everywhere in order to analyze the emerged language. And it's also called more or less a Lewis signaling game. So finally, some architecture framework in order for you to understand better the pipeline that's coming up in a bit. The first one is really trivial, image captioning. I think most of you are familiar with it. It has been an active field since 2014, has strong and defined benchmarks, and the task is basically given an image. You ask the model to come up with a proper caption. So as you can see here, the pipeline works in this way, has an input as an image, and then outputs a text. And again, you have a lot of data sets, a lot of different architectures, because it has been a really active field since 2014. So it's now 8 years, a long time. On the other side, you have DALL-E. DALL-E is a model which takes as input a text prompt and generate an image, as you can see on the example over here. The architecture is kind of complex. I will not explain it, but it's a mixture of GPT-3, VQBI, and Clipler anchors. And it has been released by OpenAI, released more or less. You have no data set, nor model weights, but the paper has been released and published by OpenAI. And so, as you can see here, the pipeline is kind of reversed. You have text as input, and the model has to output an image which is coherent with the prompt. And also, you probably heard about it, DALL-E 2, which came out some weeks ago, or one. This is one of the images generated by DALL-E 2 as an astronaut with the prompt, an astronaut on a horse in space. And as you can see, the capabilities are amazing compared to the old one. But one thing I really want to stress out is it's the example here they show on the website from the in-painting. As you can see here, the task is to in-paint a flamingo in the image, and it can be in-painted either in the pool or outside. And the model actually understands that it's a flamingo in a pool, in a house, it's most likely to be an inflatable one, while the one outside are generated as real image, a real animal. And to me, this actually expresses it makes it clear that model has some kind of concepts inside it. It can understand these similarities, this likelihood under the umbrella of image generation. Okay, let's finally switch to the actual pipeline, which I call Emergent ImageNation, or EmIn for short. And the framework is the same as we saw for the referential game, actually. So this pair of the image captions are coming from the COCO dataset. It's just a random one. And you have them as an input to a sender, which is now a DALL-E model. So as we said before, the DALL-E takes as input some text and it generates an image over here. And this is actually a real generated image. You can do the same on that GitHub repo. And you come up with, as you can see, there's already some similarities between the two images. For example, the grass and also maybe a dog-shaped head over here. But yes, then you get this image and you feed it to the receiver, which is now an image caption model, and you get an output, a text output. And again, you can do this online. And then you compare the generated caption with the gold standards. And here I call it text loss just to be as generic as possible. You can use anything over here. It also depends on the kind of output you are desired for the image captioning part. But as you can see, for this one random sample and two random repositories, we already have some kind of matches. You already have the grass in common for both captions. And also, in order to ground this image to something more real rather than just random noise, which is not interpretable by human, you can actually ground also the generated image to the golden one through another really generic image loss. So this is the actual pipeline, the whole architecture. It's just in this picture, it really resembles what the Emergent Communication has done so far. But let's now focus on why. Why is this relevant? But first sponsor, I'm using the egg library for the whole egg library, Emergence of Language in Games. It's a library in PyTorch for emergent communication, but it also actually allows the emergent imagination pipeline. It's really nice, and I like it. So research lines. I have here a few research lines, and we'll try to be as fast as possible. And the first one is just pre-training for DALL-E. At least when I wrote this, DALL-E was not available, still not available, but now we have also DALL-E 2, which is not available. So a pre-train pipeline for DALL-E, where you can actually make up for not having the dataset by population, by a population method where you have different senders trained on different image datasets, different receivers trained on different language captions, and then you just let them interact between each other, and you bring some of the knowledge coming from this different population of datasets and language models in the loop. And that should account for the lack of real dataset that we will never have access to. I also want to stress that this is the same pipeline applies to also to the emergent communication, but in here it's really the focus is for training a DALL-E model. Next, something more, let's say, something cooler, at least in my opinion, you have that for human babies, it takes 5 to 9 months to start vocalizing. And the vocalization are just baba, dada, and yeah, as you can see. So that means that for the first 5 to 9 months, there is kind of a pre-training on sensorial input. And one of the most used sensorial input in humans is vision. So what I'm actually trying to get to is that the emergent imagination can be used as a pre-training to ground the visual domain into models before for the emergent communication training pipeline. So what I'm expecting here is to actually to have the model understand the world, the real world, through images, and then learn to communicate them with actual words. What else? Also, we have a new point of view on emergent communication. This is maybe a little specific for the one that knows about the field, but I'll try to keep it as general as possible. So you have we already know that there's a big difference between artificial and human brains and their way to learn. And the EmCom field actually has a lot of problems, has highlighted a lot of problems, which sum up to the concept that language does not emerge naturally in machines as it does for humans. And you have lots of problems over here. And these problems are really difficult to analyze because usually these languages are just vectors of numbers. And so you have to come up with metrics and you have to understand what the patterns are. But what I'm trying to advocate here is that the emergent imagination and the EmCom are the part of a bigger set of machine emergence. So with this kind of new study on emergent imagination, you can actually probably see the same patterns that comes up in emergent communication through a different perspective, a different point of view, which is the one which is a visual point of view. And this can shed new insight on the same problem and maybe help us with all the issues of emergent communication. Last one, and then I'm done. It's also the one I care about the most is communication as a concept. You know, a picture is worth a thousand words. We all know that, and 70 to 93% of all communication is non-verbal. So what I really like how I like to prove my point is with an example. So lost in translation, you have here different words which can be described with English sentences. Paciocone, a plump person with a jovial and good-natured appearance. But also when you Tartle and Sobremesa, when you actually pair it with the image underneath, together with the text, the description and the feeling and everything becomes much more clearer. In order to communicate, to express the actual experience of sobremesa, the moment after eating a meal, when the food is gone but the conversation is still flowing. You can understand from the caption, but I feel that having both caption and image together really expresses something more. A practical example would be with air traffic. Right now, this is on the left, there is an airport air traffic view, and on the right, the number of messages, actually a subset of the messages logged every second. It's gigabytes file every hour. And this can be done for airplane and aircraft, but now for drones, which have been which are being used more and more every day, this is not something acceptable because it takes much more time and it cannot be fully automated. So what I'm saying is like the message part can be automated. You have protocols for drone, but I'm also advocating for more image image related and vision related communication. As you can see on the left over here, from which you can really understand what is going on rather than reading the messages. So yes, this is everything. The code is available over here. It's, as I said, it's based on PyTorch and Egg. And that's it for me. Also, bibliography for the one interested.